Bismillahirrahmanirrahim. Assalamu alaikum students. So this lab is about comparators. The main objective is to understand the operation of comparators and simulate the given tasks in Allen Bradley PLC. So what are comparators and how do we implement them in a PLC Logix Pro? So this lab would give you the definition of comparison instructions and the way they are used. In general, comparison instructions are used to test a pair of values to energize or de-energize a rank. So we'll move forward with the commands. Following is a list of comparison instructions. EQU, this stands for the equal comparator. It checks for the sources that are equal. And then is NEQ, this is for not equal sources or preset values. Then is the LES, less than, and the LEQ, less than or equal. Then we have GRT, which says greater than, and then we have GEQ, greater or equal. So let's start with the equal one, EQU. So it says that here's the symbol for the equal one, and it says that it tests whether two values are equal or not. So here's the source A and here's the source B, which is being fed the address, or it can be fed a constant, but there's a condition that on source A there must be an address. So you can't put a constant over here, but you can put a constant in the source B place. You can also put an address over here, but putting a constant in the source A place is not a good option. So here's the comparator for equal testing command, and this checks whether the two values coming from the two sources are equal or not. And here it says negative integers are stored in 2's complement. So I guess that's pretty much easy to understand that how does this operate. NEQ, that's for not equal, and here it says source A, again an address, and source B can be an address or something that you can put it in as a constant. So this tests whether one value is not equal to a second value, so it will result in a positive output only if the two sources are not equal. Then we have the following instructions about it. If source A and source B are not equal, the instruction is logically true. If the two values are equal, the instruction is logically false. Source A must be an address, it's the same as the equal one, and source B can either be a program constant or an address. Negative integers are stored in 2's complement. It's pretty much same as the equal one comparator. It's just a little different from it, that the source A and B need to be unequal for a positive or high output. Then we have less than, LES, and here's the symbol for it. Now you would be confused about the thing that whether it checks the B is less than A condition or A is less than B condition. So we should be clear about it, that it checks the A is less than equal to B, A is less than B condition. So if source A is less than the value at source B, the instruction is logically true, and if the value at source A is greater than or equal to the value at source B, the instruction is logically false. Again, it says the same, source A must be an address and source B can either be a program constant or an address. Negative integers are stored in 2's complement. Then we have less than or equal. So it checks whether the source A is less than or equal to the value at source B. The instruction would be logically true if A is less than or equal to B. And if the value at source A is greater than or equal to the value at source B, the instruction would be logically false. It repeats the thing that source A must be an address while source B can either be a program constant or an address. These things would be clear to you once I would present an example at the end of these instructions. So then we have GRT. It checks whether the source A is greater than the source B or no. So if the value at source A is greater than the value at source B, the instruction at output would be logically true, and if the value at source A is less than or equal to the value at source B, the instruction would be logically false. So it repeats that source A must be an address, while source B can either be a program constant or an address. Negative integers are stored in 2's complement. Then we have greater than or equal to. So it's the same way where we had less than or equal to, and now we have greater than or equal to. So it says that if the value at source A is greater than or equal to the value at source B, the instruction is logically true. And if the value at source A is less than to the value at source B, the instruction is logically false. And again, source A must be an address and source B can either be a program constant or an address. So the negative integers are stored in 2's complement. These are all the same instructions, only the way these comparators perform these instructions are different from one another. Now we are moving to the lab tasks, but before we move to the lab tasks, we'll complete an example. I have made a circuit for you guys. So here you can see that I have implemented 3 rungs over here. The rung number 1, which has the address 000, has a counter up. You can see C51 is the address assigned to this counter by me. I have assigned the preset value 10 to this counter, and then I have connected this to an input switch where the address is I1/0. This means this is the switch. Okay, so you can see that here I have placed a comparator. And where do I get this comparator? I'll go offline. Here you can see you have a compare option. So when I click on it, it shows me a list of comparators, and the one I have chosen is the EQU, which is the equal comparison maker. So I'm using the equal comparator over here, and to this comparator, here's the source A and the source B. In the source A option, I have inputted C5:1, which is the address of this counter, and then .acc, which is for the accumulator value. So I have inputted the accumulator address over here. So when the accumulator will change its value, the comparator would get the information for source A over here. And similarly, in source B, I have placed a constant value 5. Okay, so here's the address for a counter up, and here I have inputted a simple constant 5. Then is the reset button for this counter up, and you can see that I've placed a normal switch for it in the typical way that we have been doing in past. So I guess that's pretty much clear. Now we'll move towards downloading it to PLC, and now I'll go online with it. I'll just run it. Okay, so accumulator is set to 1. I'll first of all reset this value. Okay, so the accumulator has been resetted to 0. Now let's see what happens. The source B is 5. The source A, which is this counter up accumulator value, is 0. Now I'll make this switch on. You can see the accumulator has shifted towards 1. I'll turn it back off. You can see that this comparator has got this information that accumulator is now 1. I'll again turn it on. Accumulator is now at 2, you can see the information over here is at 2 2. So I'll turn it off, I'll turn it on again. You can see the information that the 3 is the value of accumulator over here has been transferred over here as well, but the output of this comparator is still 0. Why? Because this 3 and 5 are not equal. I'll turn it back off, turn it on. Here's the 4. Now let's see what happens when we'll move towards 5. So what happened is that accumulator over here has reached the value 5, and this source B and source A have become equal, and thus the comparator is giving a logically high output. Now if I turn it off and turn it back on, the accumulator has got the value 6, which is not equal to the source B value 5, and thus our output switch has turned off. So that's an example I wanted to present to you guys. I guess that would be pretty much easy for you, and that's not something really hard to understand. So I hope inshallah things would get easy for you. So here are the lab tasks. Exercise 1 says consider a system in which we have a switch to turn on light and fan. Light goes on when switch is pressed 5 times and fan when pressed 10 times, and also a reset switch. I guess I have already done this task for you. So you have just to change the figures for accumulator and preset and the counters. Then is the exercise 2, traffic control using 3 lights. From the simulations menu at the top of the screen, select the traffic light simulation. Okay, so here's the simulations menu, and you can see that here's the traffic simulator. Okay, so it says using your knowledge of timers and comparison instruction, develop a ladder logic program which will sequence a set of green, amber and red lights in the following manner. Light O2/00 red should be on for 12 seconds. Light O2/02 green should be on for 8 seconds. Light O2/01 amber should be on for 4 seconds. The sequence now repeats with red is equal to on. Okay, so this is for the traffic light signal, and you have just to choose this simulator over here, which is the, I should go back to the offline mode. I'll go to the simulations, and here's the traffic simulator. Okay, so here's just a different simulator in a different look. You shouldn't be worried about it. Once you will change the circuit over here according to these addresses, you'll get to know about the things. So here's the O200, O201, O202, which is basically this red, green and amber light. And what we have over here, is that this O2/03 is the don't light over here. And are we using it over here? No, we are not using it over here. So this is the sequence that you need to repeat for the red, green and amber, 12, 8 and 4 seconds. Then is the traffic control using 6 lights. Modify your program so that the 3 lights which represent the other traffic direction are also controlled. So what are the other traffic lights? It says O2/00, O2/01, O2/03, and here we have input 1/02, 1/01, and now you can see that here are 3 more lights over here for the next direction. So you have to control these as well. I don't think that's something rocket science or very hard to do. So here are the sequence and timings for these 3 lights as well. Now the last exercise says modify your program so that there's a 1 second period when both directions will have their red lights illuminated. Note that there are actually 2 such overlaps that need to be accounted for. The timing diagram below shows the 6 discrete timing intervals required to accomplish the desired sequence of operation. So, the main thing that you need to do is that there should be a 1 second period when both directions will have their red lights illuminated. So for this task they have given a different timing diagram that you need to implement for the 6 lights that are present on the signal, and that's how your lab tasks get completed. I hope things would be clear to you, and these are very easy to understand. I hope you'll implement them and try to submit the reports in time. So take good care of yourselves. Take care. Allah Hafiz.